consider a situation where you have a system of two particles such that the particles cannot leave or enter the system. And also, there is no net external force acting on the system. Then, if you take Newton's equation for the second law and put F net is equal to 0, what you get is dP upon dt is equal to 0, which basically means that P is a constant. Well, the same thing said in simple words is, if no external force acts on a system of particles, the total linear momentum P of the system will not change or remain constant. And this is what we call the law of conservation of linear momentum, where the word conservation means maintaining or preserving a state. In this case, preservation of linear momentum. And you will see as we progress, it is a very powerful tool for solving problems in physics. So you could also state the same law as initial momentum at some time will be the same as the final momentum at another time, provided there is no external force acting on the system and the system is isolated. And these are two standard conditions that always apply when we're talking about conservation of momentum. Now, two important things to remember. One, this is a vector equation and particles could very well be moving in three-dimensional space. Therefore, you could say that this equation can have three equations, each corresponding to the conservation of momentum in three perpendicular directions in an x, y, z coordinate system. And therefore, momentum must be conserved in each of the x, y, and z directions as well. 2. If the net force is not zero, it is possible that linear momentum may be conserved in one or two directions, but not in all directions. So let us say the net external force on a closed system is 0 along an axis. Then the component of the linear momentum of the system along that axis will not change. But if the force is not 0 along another axis, the linear momentum of the system along that axis will change. So, as an example, let us say you throw a duster across a classroom, and while it is in the air, we know the only external force acting on the duster is a gravitational force directed downwards along the y-axis. So, since there is an external force acting on the system, that is your duster, the vertical component of the linear momentum of the duster does change along this axis, simply because the velocity along the axis is constantly changing because of the force. However, as we learned in projectile motion, there is no horizontal external force acting on the duster and its velocity remains constant along this axis. And therefore, the horizontal component of the linear momentum does not change. So, here is a situation where even though an external force is acting on the system, momentum is conserved along one of the axes, but not along the other axis. Another thing I want you to note is that we mentioned only the external forces acting on a closed system, even though the internal forces can change the linear momentum of portions of the system. But they cannot change the total linear momentum of the entire system. As an example, there are a lot of forces acting between the organs of your body, but you see, they do not move you across the room. And the reason for this is that all internal forces come in Newton's third law pairs. That is, for every force, there will be an equal and opposite force, and the two will cancel each other, thus making the net force 0. So if you're liking this video that really took a lot of effort to put together, hit the like button. It really helps the channel. And with that being said, let's move on. So with this in the background, let us study 3 types of collisions and what happens to the momentum of the bodies under each type, with the assumption that there is no external force acting on the system. So the first one is inelastic collision. So there are two conditions that need to be met to call a collision inelastic. Number one is, when such a collision happens, total linear momentum of the system is conserved. That is, it does not change. And condition two is, the kinetic energy of the system is not conserved. That is, the initial kinetic energy is not the same as the final kinetic energy. And you can see this in everyday collisions, like two cars colliding or a ball and a bat colliding. And you see, in these types of collision, some energy is always transformed from kinetic energy to other forms of energy, usually thermal energy or sound energy. And that is the reason the kinetic energy of the system is not conserved. So, if these two bodies that form our system, that is closed and isolated, we can write the law of conservation of linear momentum as total momentum Pi before the collision is equal to total momentum Pf after the collision. Or writing P is equal to mv, we get m1 v1 initial plus m2 v2 initial is equal to m1 v1 final plus m2 v2 final. Second type of collision is called completely inelastic collision, which you can say is a special category of inelastic collision. So in a completely inelastic collision, three conditions are to be met to call it completely inelastic. The first one is, after the collision, the two bodies stick together and then move as one single body. The second is, the linear momentum of the system is conserved. And the third is, kinetic energy is not conserved. In fact, the loss of kinetic energy is maximum in this type of collision. So what we have here are two bodies, and we see mass m2 initially at rest, and after the collision, mass m1 sticks with mass m2 and the two masses move with a common velocity v. So if the linear momentum of the system is conserved, we can write m1 v1i or initial is equal to m1 plus m2 v final or the capital V, or v is equal to m1 upon m1 plus m2 into v1 initial. So an interesting point to note is that v will always be less than v1 initial, because you see the ratio m1 upon m1 plus m2 is always less than 1, meaning that multiplying this ratio by v1i gives a value less than v1i. The third category of collision is elastic collision, and in this category of collision, the two conditions that need to be met are: one, the momentum needs to be conserved, and two, the kinetic energy is also conserved, that is, it is the same before and after. But you must note that here the kinetic energy of each colliding body may alter, but the total kinetic energy of the system will remain constant. So, as we discussed earlier, everyday collisions are often inelastic, but some of them can be approximated as elastic, which means that we can approximate the total kinetic energy of the bodies that collide as conserved and not transferred to other forms of energy like sound and heat. A good example is the collision of a cue ball with another ball in a game of billiards that can be approximated as being an elastic collision. Well, you do hear the sound of collision, but the energy wasted in this sound is very, very low. Now, before we wrap up this lesson, it is important to have a quick look at what happens to the velocity of the center of mass of the system. So, in a closed, isolated system, the velocity of the center of mass of the system cannot change because of a collision, simply because it is a closed system and there is no net external force to change it. And to get the expression for V center of mass, consider the same two-body system. We can connect the V center of mass to the total linear momentum P of the system by writing P is equal to m times V center of mass, which can be written as m1 plus m2 times v center of mass, or v center of mass is equal to p upon m1 plus m2. Now we can write this p as p1 initial plus p2 initial. And you can see this expression is constant since both the numerator and the denominator are constant. And so v center of mass has the same value before and after the collision. So this lesson was about the three different kinds of collisions that happen in nature. In the next lesson, we'll focus on elastic collision and how the velocity of the stationary target changes depending on its mass. So if you like the lesson, do give a thumbs up. That'll be helpful, and I'll see you in the next lesson.